So we have been talking about the crisscross method for writing formulas for ionic compounds. And so let's use sodium oxide as an example. So let's say we wanted to write the ionic or the formula for this ionic compound. We would need to know the charge of the sodium cation, Na plus. So we would look at the periodic table, or where sodium is on the periodic table, and where oxygen is on this periodic table, and to determine the charge that of these ions. And then we could use the crisscross method. And based on this, we would know that there are two sodium cations for every one oxygen or oxide in the formula unit. And the formula unit of sodium oxide. And so the significance of this is that we have 2 to 1. And I wanted to highlight or further highlight in this video that we need to balance the amount of positive with negative charge overall. And that's the way that we get a electrically neutral formula unit overall. And the crisscross method just helps us to do this. And so we may start to do this kind of blindly. We just, okay, crisscross the charge, but this is what essentially the crisscross method is helping us to do. But conceptually, it's important to think about why we're doing this. So it's allowing us to uh, figure out how many of each of these ions we need to get an electrically neutral formula unit. And so, representing this using these diagrams. So we see that in Na2O, we would have, so that would give us a total of 2 plus, and so 2 of those, so 1 plus and 1 plus gives us 2 plus, and one of these oxide anions would contribute a total of negative 2 charge overall. And so we see that the charge, positive and negative, are exactly balanced. And so overall, we get this electrically neutral formula unit. And so the crisscross method just helped us to do that more easily. And then here for magnesium oxide, so again, we could use the crisscross method, Mg2 plus and O2 minus, and we would determine that we need to give us an electrically neutral formula unit, we need 1 and 1 of those. So 2 plus and 2 minus, but then we said when we were discussing the crisscross method, anytime we had the same magnitude but opposite charge, that we would always get a 1 to 1. So 1 1-to-1 ratio. So when no subscript is written, that means we have 1-to-1. So MgO. And then, so we know that so unlike for sodium and magnesium, so those are in the groups where we have these predictable charges, these ones here in the middle, so the transition metals, can form ions or cations with variable charge. So some of them can form compounds or cations with variable charge, and that leads to different ionic compounds. And so we need to know which cation was involved in the formation of that compound. Now, there are some that tend to form one cation more consistently over another, or one particular cation most consistently. So, for example, silver is almost always +1, zinc is almost always +2, and cadmium is almost always +2. And so for those ones, we don't technically or typically indicate the Roman numeral. And again, we use Roman numerals whenever we have these transition metals that tend to form cations with variable charge. We use Roman numerals to indicate the charge. But for the ones that consistently form cation of a particular charge, we tend not to use Roman numerals to indicate the charge. Um, but rather than trying to undo the crisscross, so maybe a better strategy might be to think of it conceptually. To so so knowing that we need the same amount of charge, of positive and negative charge, so that might help us to more readily determine the charge of the thing that's not known, rather than undoing the crisscross, which gets a little bit complex sometimes. So to think about the transition metal that's unknown. So copper is one that forms variable charge. So it's one that we'd have to think about the charge that of the cation that was involved. But to do that, we rely on the one that is known consistently. So we rely on the charge of the anion that's known consistently. So sulfur is in group 6, and we know that it always forms a charge of -2. And based on the subscripts involved, we know that there's a ratio of 1 to 1. So there's one sulfur, or sulfide anion with a charge of -2. And so there's a total of -2 charge. And we know that there's one of these copper ions. And so then, in order to have equal amount but opposite charge, so equal quantity but opposite in charge, so a balance in the amount of positive and negative charge to give us an electrically neutral formula unit, then this has to be +2. So this has to be copper 2 sulfide. And so we would name this as copper 2 sulfide. And so again, the Roman numeral would indicate the charge. And we only use the Roman numerals for those ones that, or those transition metals that tend to form variable charge. So we don't use them for the Roman numerals for the group 1 and group 2 metals, for example, or elements or atoms that form an ion of a consistent charge. And then here, so we have chloride, so we know the charge of that, and we're going to use that information, what we know, to help us to determine the charge or the original charge of this copper cation. We have two of those, and so 2 to 1. So two of these chloride anions. We know that chloride is always -2, or sorry, -1. So two of those, and always -1. So that's going to give us a -2 charge overall. What's the charge of copper? We don't know, but we can figure it out based on there's only one of those in the formula unit, and we have to have a balance in the amount of charge. So then this must be +2, and that's a little bit easier than undoing the crisscross. Here, so now we have two of these unknown copper cations and one of our known oxide anions. And here we have -2. And so then, what did you say? So we have a total of +2. We need a total of +2, but each of these must be +1, right? So then this must be copper 1 oxide. So copper 1 oxide. And then this would be, so this on its own would give the 2+, since there's only one of those, so this would be copper 2